So in this problem, we're going to think about what happens when you are on a loop in a roller coaster. So we're going to imagine that the object of interest is a little roller coaster car that's at the top of the loop. Okay? Now, we know the radius of the loop, and we know how fast the roller coaster is going. We know its velocity. It's moving in this direction with a velocity v. And I want to know what is the apparent weight. So in other words, what is the normal force? So what I'm going to do is I'm going to draw a free body diagram of what's going on right here. Okay, so I'm going to go ahead and draw it on top of this thing just to kind of show you. Gravity, of course, pulls down on the roller coaster and the person that's in it. The track also pushes on them, and the track can only push perpendicular, so there's actually a normal force going that way. Okay? So I want to know, what is that normal force? Now you say, well, there's no forces pushing up. That's true. But because this is moving in a circle, there needs to be an unbalanced force pointing towards the center of the circle. So the weight and the normal force are the forces that keep this object moving in a circle. And we got to figure out how big the normal force is. Okay? So let me just be all proper here and draw a real free body diagram. Here's the object of interest. There are two forces on it. mg points downwards, as does the normal force. And those are the only two forces on it, okay? We're ignoring friction. All right, so what we're going to do is we are going to apply Newton's law. Newton says that the unbalanced force acting on an object equals its mass times its acceleration. Okay? Now, the unbalanced force is going to be these two forces, and they both point downwards. So I'm going to, for the sake of my problem, call this the x direction, because that's the direction it's accelerating. Remember, it's easiest if you make the x direction the direction of acceleration. So if I make the center of the circle the direction towards that, my x direction, then the forces in the x direction are F sub m plus mg. Those are both going in the x direction, and they have to equal the acceleration in that direction. Now, the roller coaster is actually moving sideways, but it's moving in a circle, so the acceleration is perpendicular. It's towards the center of the circle. So the acceleration is going to equal m times the centripetal acceleration, which is v squared over r. So this is how I can apply Newton's law to get my equation. Okay? Now, if you don't like doing it that way, you can always just assume that up is the positive direction, and then when you apply Newton's laws here, you would have something that looked like this. So this is kind of the alternate explanation. Gravity is going down, so that's minus mg. The normal force is going down, so that's minus F sub m. So that's the net force, and that equals the mass times the acceleration, which is mv squared over r. But the centripetal acceleration points to the middle of the circle, which is always also the negative direction. So this equation and that equation are completely equivalent. Okay, it doesn't matter which way you choose as long as you're consistent. All right, so now that we have this, we can solve for the normal force. The normal force will equal mv squared over r minus mg. I can plug in, well, actually I'm going to factor out a mass, and I'll get v squared over r minus g. That is the normal force. And then, of course, you can plug in all your numbers to get the answer. So I get this expression when I plug in all the numbers that I got, the mass, the radius, the velocity, and then I can plug that in my calculator, and I can calculate a value of 47 newtons. Okay? Now, normally, a person who has a mass of 100 kilograms has a weight of 980 newtons. So not only is this normal force pushing down on them, but it's very small compared to their weight, which is why at the top of a roller coaster, you feel close to weightless. What that really means is you feel close to normal forcelessness. So there you go. That's how you solve that problem. Okay? Now, a similar problem says, what happens if you are at the bottom of the loop? Okay? So now let's figure out what happens at the bottom of the loop. Things are slightly different here. I'm going to use my mug again to draw my roller coaster loop. So we are looking at the bottom of the loop right here. So two things happen. First of all, you're going faster, right? So some of your potential energy from the top of the loop was converted to kinetic energy. So we're going faster. So our velocity is now 12 meters per second. We're moving in this direction. And if I look at the forces on the roller coaster right there, gravity pulls down still. That's mg. But now the track pushes up with a normal force, F sub n. And the center of the circle is up here. So the acceleration must be pointing upwards. You're moving in a circle. The centripetal acceleration is perpendicular, pointing towards the middle of the circle. So the acceleration is pointing upwards. So that must mean that the force going up is bigger than the force going down, because the net force has got to point towards the middle of the circle to make you move in a circle. So if we apply Newton's law now, we can say the force going up, F sub n, minus the force going down, mg, equals the mass times the acceleration. The car is moving sideways at this point, but because it's moving in a circle, the acceleration is upwards, and that's v squared over r. So what we're saying is the normal force has got to be bigger than mg, so that you have an unbalanced force that equals mv squared over r, the centripetal force. It's the difference in these two forces that make you move in a circle. And so you can quickly solve for the normal force. That's going to be mv squared over r plus mg. And I'm going to go ahead and just calculate these parts here. So when I calculate mv squared over r, that's the centripetal force. You need 4,114 newtons of centripetal force, plus you need 980 newtons of force due to mg. And so the normal force, the force pushing up on you on the bottom of the roller coaster, is actually closer to 5,094 newtons. Okay? And so that is the force pushing up on you at the bottom of the roller coaster. And if you've ever ridden a roller coaster, you know that at the bottom you feel really heavy, right? That's because the force pushing up on you is very large. It's not because you have any more mass. It's because the normal force is larger on you. That's the apparent weight. A lot of times, this number here isn't very meaningful, so we express it in terms of your normal everyday weight. So if I take your normal force, 5,094 newtons, and I divide it by what you usually feel when you're not accelerating, which is 980 newtons, I get a value of 5.2. And this thing, 5.2, we call it the g-force. So at the bottom of this roller coaster, you experience a g-force of about 5.2 g's. So 1 g is just your normal weight. If you felt a normal force of 2 g's, that means the normal force on you is 2 times your normal weight, or 2 g's. And so in this case, you can quantify and say at the bottom of this roller coaster, you feel a force of about 5 times your normal weight, or 5 g's. So it's helpful to know that the g-force is really just the normal force divided by your everyday weight, mg. Okay? And of course, if those two are equal, the g-force is just 1. That's what you feel standing still on the ground. Okay? Okay, so you should be able to solve the rest of those. Wait a minute, I just fell off the page there. So yeah, the g-force is the normal force divided by mg. Okay, so if you know the g-force is 10, if the astronaut experiences a g-force of 10, then you know their normal force is 10 times greater than their usual weight due to gravity. Okay?